Greetings. So this is our next video. Just going to quickly show just the similarity between what a gradient looks like and how it is a type of vector field. So this particular function we have here, g of xy is equal to the square root of x squared plus y squared, is our function. You'll later on find out that there's a particular name for this type of function. And so the gradient of this function looks like this: del of g of xy equals, and the first component will be the x partial derivative, which in this case is 1/2 quantity x squared plus y squared to the negative 1/2 power multiplied by the derivative of x squared plus y squared, which is 2x, and then the y component, which is very similar to the x component, is going to be 1/2 quantity x squared plus y squared to the negative 1/2 power multiplied by 2y. And that's your vector. So as you recall, I have a couple of conditions for how we leave our solutions, and one of them is, simplify or reduce the actual fractions if possible. But let's get rid of that negative exponent in the expression, so that gradient would become x over, and you can either write it in a square root or in a quantity, square root x squared plus y squared, comma, y over square root x squared plus y squared. And there's your two components. So this would be called the gradient, or the vector made by the partial derivatives. So the vector field notation we've seen in the textbook is to just use a different naming at the beginning, but call it capital G of xy equals, and the same two components we just wrote down, x over the square root x squared plus y squared, that's messy, sorry, comma, y over the square root x squared plus y squared. So this is an example of a vector field that was came from, or was born from, the gradient of a function. There we go.